problems, and some of the artificial intelligence techniques can be solved in this MATLAB containing the programming part and the Simulink part. In the programming part, we can write the code as nearly equal to the high-level languages or C and C++, Java. So many languages are there. In those languages, we have the number of drawbacks are there. Most of the electrical engineering problems are variables are complex related variables. And suppose if you use the C language, we don't have any complex function. And we don't suppose if you want to perform the mathematical calculations, especially electrical engineering complex analysis, it's a complicated task. And the length of the code is also more in the case of traditional languages or C and C++. Some of the languages are there. And by make use of MATLAB, we can solve the number of problems by make use of the just like built-in functions. Okay, here coming to the introduction to the MATLAB. MATLAB means a matrix laboratory, which includes the vector manipulations, matrix manipulations, built-in functions, and M files. The script files are represented in .m files, Simulink, which we can include the modeling examples. Here the two parts. The MATLAB contains the vectors and matrices, built-in functions, M files, scripting functions can be represented in MATLAB, and Simulink modeling examples are represented by make use of the Simulink. And here our working directory. Here the first one is the file, edit, debug, desktop, Windows. We can see the MATLAB front first screen. File, it contains the file, edit, debug, desktop, window, help, and here is the command window. And here the all files are shows on the .m and MDL. And older versions, Simulink files are represented in .mdl files. Now SLX files, the latest versions. Now MATLAB version is 2021B. In that, Simulink files are represented in SLX. Okay, strengths and weaknesses of the MATLAB. Okay, MATLAB behave as a calculator or as a programming language. And MATLAB, it can combine calculations and graphic plotting. Normally, the MATLAB is easy to learn. Why? Because suppose to perform the inversion of matrix in the traditional languages C or C++, we have to write the length of code, more than 20 lines of code you have to written. But in this case, only one built-in functions, inverse, only the built-in function, inverse function can inverse the particular matrix. And it's not compiled. We can fix the errors easily. Optimized to be relatively fast when performing matrix operations. MATLAB does not have some object-oriented elements. And the weaknesses of the MATLAB is not general purpose language such as C, C++ or Fortran. And MATLAB is designed for scientific computing. This software may not be useful for all other applications. Interpreted language, slower than the compiled language, and commands are specified MATLAB usage. And actually, one drawback is, suppose if you design a Simulink file, one version, that is lower version, the file may be executed in the higher version. Normally, the higher version of a Simulink file may not be executed in the lower version. That is one of the more drawback. And here vectors and matrices can be represented by, suppose if you represent the 3 by 3 matrix, so we can use A is equal to 1, 2, 3. That is, we have to use the semicolon that indicating that neuro operation. Okay, here A is equal to 1, 2, 3 and 4, 5, 6 and 7, 8, 9. These can be represented by make use of the cursor. We can write the cursor. The statement is looks like this. Then you can get the answer is 3 by 3 matrix. It's a simple representation. In C language or C++ language, you have to represent to access the matrix. You have to write the lengthy code. But in this case, directly you can use this MATLAB command prompt. Just you enter just simply a calculator. We can utilize the calculator like that. So multiplication A star 2 and A by 3, that is divided into 3. Here is the MATLAB matrix 1, 2, 3, 4, 5, 6 and 7, 8, 9. This A into 2, that means each and every element multiplied with 2, and A by 3, each and every element divided by 3. And every entry, performing operations of every entry. Here the square, every element in the A is the dot cap 2, that indicates the square of the matrix. Okay, see here is the dot indicates that every element squaring. Suppose if you want to perform the multiplication operation, if the dot is missing, then automatically we can, that is the product operation. See the difference between, after learning the built-in functions, how you can utilize the functions. That is the important task here. Here is the first one is the dot is linked here. That means A dot square, that indicates each and every element squaring. But in this case, A into A, this is the product function and this is the individual element. Suppose if you want to consider the individual element in the matrix, you have to use the dot. So this is A star B. See here the result is looks like here. A star B, A dot star P. That means individual element multiplied with individual element. Here A dot square means this is A into B. This is a scalar quantity, but this will give the error. Okay, arithmetic operations on make use of the matrices. Here consider the one example, our electrical engineering example. Calculate V1 and V2. Here the point, this is here in this location V1 and this is V2. So similarly, we can write the equations like this. So 0, 0.1 plus J 0.2 V1 minus J. This is the expressions we are prepared by make use of the nodal analysis. Yet this problem can be solved by make use of the nodal analysis. The node equations are written as per the KCL Kirchhoff's current law. This problem is written like this. This is the matrix A. It's containing 0.1 plus J 0.2 and minus J 0.2 and minus J 0.2 plus 0.1. This function can be solved by make use of our MATLAB. Here A is equal to, in this case, the first element 0.1 plus 0.j. The second element is minus 0.2j, And the second row, first element is minus 0.2j and 0.1j. Then we can use the x is equal to inverse of a star y. Then we can get the node currents. Sorry, here node voltages. Here script files, .m files. These are model files or .m files. Script files are extension is .m with extension m. The script files includes the some specified plot functions and generalized functions, built-in functions, and command functions, and subfunctions can be included in the script file. Okay, this is a MATLAB editor. In the editor, you can type the commands, then you can test the function by make use of the, here is the input, the function. Normally every program it requires the input parameters as well as the output. It will get the output parameters by make use of the functions which are represented in our software. Normally the function contains the commands, functions, intermediate variables. By after processing, finally it will give the output. Okay, here every function must begin with a header. Function output, function name, and input arguments to be represented in the braces. Function output, function name. Okay, here the next part is the Simulink part. In the Simulink, this is the window. This is MATLAB window. Here the command window. Suppose if you type the Simulink, then it will open the Simulink, or otherwise the top corner one icon is there, Simulink icon is there. If you press the icon, it will open the Simulink. Okay, here so many library functions are available in the Simulink library browser. The first one is the commonly used blocks, continuous blocks, discontinuous discontinuities, discrete, logical and bit operators, lookup table, math operators, model verification, model wide utilities, ports and subsystems, signal attributes and signal routing, sinks and sources, user defined functions, additional math discrete functions. So in the library Simulink composed of different types of blocks are available. By make use of the Simulink blocks, you can set the functional parameters, and then we can run the simulation diagram, then you will get the result. Okay. And the library, basically our electrical system containing the only electrical blocks can be accessed by make use of the SimPower systems. In the SimPower systems, the first one is the application libraries and electrical sources, elements, extra library, machines, measurements, and power electronics. In this case, the measurements, we need the current measurement, voltage measurement, load flow bus, and three-phase VI measurements, and multimeter. These are the blocks available in the SimPower systems measurement block. And power systems and power electronics block itself, it containing the our detailed thyristor, diode, GTO, IGBT or diode, ideal switch, MOSFET, 3-level bridge, thyristor, and universal bridge. These are the components are available in our SimPower systems library. And power system electrical sources are AC current source, AC voltage source, battery, controlled current source, controlled voltage source, DC voltage source, and three-phase programmable source and three-phase sources are available in the sources electrical sources library. And elements library, SimPower systems elements library, it's composed of the breakers, three-phase breakers, single-phase breakers, and connection port, distributed parameter line, grounding transformer, linear transformer, multi-winding transformer, mutual inductance, neutral, parallel RLC branch, parallel RLC load, pi section, single line, or three-phase line saturable transformer, series RLC branch, series RLC load, surge arrestor, three-phase breaker, three-phase dynamic load, three-phase harmonic filter, three-phase mutual inductance, three-phase pi section line, and three-phase parallel line. These are the components available in the SimPower systems library elements block. And SimPower systems machines, we know that the number of machines are there in our electrical engineering: asynchronous machines, synchronous machines, DC machine, discrete DC machine, exciter system. So many electrical machines are available: permanent magnet synchroscope, simplified synchronous machines. These are the machines available in the SimPower systems machines library. Okay, here we can access the particular element to our Simulink diagram by clicking the by right clicking and send those blocks are transferred to the our required Simulink editor. Here is the next topic is introduction to fuzzy logic controller. We normally suppose if you want to solve any electrical engineering problem or any engineering problem, first of all you have to identify the description about the problem and then formulating the equations, and then you have to check the solution procedure. The procedure may be mathematical. The mathematical functions, based on the functions, mathematical procedures may be changed. If the problem is related to the equation related to the integration, then automatically you have to implement the integral rules, and the function is related to the differentiation, the differential rules, the differential ordinary differential equation, homogeneous, like that each and every parameter you have to consider, and each and every case the system must be solved by make use of the mathematical functions. So some of the cases we may not get the mathematical functions. Some of the realistic conditions we may not get the mathematical equations. Those cases, how you can solve without creating the mathematical equations. Such type of problems can be solved by make use of the artificial intelligence techniques. So here is the fuzzy logic and neural networks. Without preparing any equation, with the relationship between the input and the output parameters, sometimes we may not identify the equation between the input and the output parameter. Such type of problems can be solved by make use of the fuzzy logic controllers or neural networks. So without knowing the relationship, the mathematical relationship between the input and output parameters, we can solve some type of artificial intelligence techniques. Okay, here in MATLAB, we have the fuzzy logic toolbox is available. Okay, MATLAB fuzzy toolbox consisting of two useful tools, FIS editor, that is fuzzy inference system, which it can provide the powerful environment to define and modify fuzzy inference system variables. And the next one is the fuzzy controller. This is a block in fuzzy toolbox library Simulink environment. This block admits the fuzzy inference system variable and fuzzy inference system editor implement the desired rules. Fuzzy FIS editor, normally we can write the desirable rules. The rules that is a simple rules. If, then, else, and finally if x is greater than y and y is greater than z, then simultaneously we can say that x is greater than z. These type of statements we can use in the fuzzy FIS editor. Okay, fuzzy inference system containing these are the blocks available. The first one is the FIS editor. It includes the input parameters, output parameters, and rule-based fuzzy editor is there. Power. Okay, it includes the fuzzy inference system composed of these are the blocks. The first one is the fuzzy FIS editor and membership function, surface viewer, rule viewer, and rule editor. So here FIS editor, suppose if you click this block, then this is membership function, and this is the central part is the rule editor, and these are the output parameters. So fuzzy inference system, it's composed of FIS editor. The first one is the input membership function, and then output membership function, and rule editor. That means we can write the rules by selecting the input parameters, and simultaneously we can how you can get the output parameters. That is the rule framing structure before writing the rules. Okay, to implement a fuzzy inference system, first of all we have to follow the 5 steps. First one is the fuzzification using input membership functions and apply fuzzy operand. Here is the fuzzy operands are two types normally. That is AND OR operator. AND operator, which it will give the minimum value of the selected inputs, and OR operator, the maximum value of the selected outputs. Apply implication method on each rule. So you have to write the statements by if then rules. Aggregate all outputs, defuzzification of the output set. These are the 5 steps must follow the time of fuzzy inference systems used to solve the particular problem. First of all, the fuzzification, how to select the members, how to divide the members into the different classes. Then how to combine the input parameters, or how to combine the input membership functions, and how to get the output. These are performed by make use of the fuzzification and defuzzification. These two are important to solve any type of engineering problem or other problems. And the first one is the FIS editor, which containing the suppose double clicking the to set the input parameters by double clicking the input, and simultaneously if you want to set the output parameters by double clicking the output. Suppose if you want to insert fuzzy rules by pressing the central mandamni, two types of fuzzy inference rules are there, and the first one is the AND operator, OR operator. Normally AND operator, AND method, fuzzy inference systems, that just fuzzy inference systems are AND operator, we will get the minimum value of the selected inputs, and OR operator, we can get the maximum value of the input operator. Implication, minimization, aggregation, defuzzification, centrality method, we have the number of methods are there. Centrality method is preferred, and the name of the variable can be changed by adding these parameters. And we have the membership functions are different membership functions are available. Triangular, trapezoidal, Gauss, T-section, like that different types of membership functions are there. We have to select the particular membership function. You have to set the parameters as per the MATLAB based requirement. Here is the first one is here FIS variables are two input variables and two output variables are represented. Yellow color indicating the input variables, and light blue color are these indicating that output variables. So we can set the range of the parameters, and division of the range represented here. The name of the membership functions, we can change the membership function by typing here, and the parameters are represented here, and this is a membership function editor. And the next one is the rule editor. We can select the input parameters by AND or OR operator. Then after combining the input parameters or input membership function, what are the output membership functions can be generated. Previously we are analyzed that. Then you can prepare the rule list. First select the input parameters, combine the input parameters, simultaneously what is the output, proposed output may be generated. Like that you can prepare rules. Then we can prepare the rules by make use of the rule editor. Okay, after running this, here is the input parameters. Two inputs are there, two outputs are there. So by make the use of input parameters, automatically internally it will calculate, it shows the output parameters. Okay, yes, here is the surface layer. How the input parameters are input and output parameters relationship can be identified by make use of the surface viewer. Okay, here FIS editor benefits are simply add and remove the inputs and or outputs. We can add the input and or remove the inputs and or outputs. Set the modify the interference methods. That means interference method means by adding the parameters we can use AND operator or OR operator. In the set theory, intersection and union. The similar fashion, this is binary variables like OR operator and AND operator. And set or modify the inference methods. Simply add and remove the membership functions and easy management of functions parameters. And the next step is we can easily frame the rules, and we can modify the rules according to our requirement. We can change the rules. Great visualization area of FIS diagram, 2D visualization of inference of for any input pairs to any output. Okay, we can create the input parameter relationship between the input parameters and the output parameters without knowing the particular convolution equations. That is one of the benefit in the FIS editor system. Okay, we have the two inference engines are there, Mandamni and Sugno. Okay, this Mandamni, we have to write the rules as per the Mandamni inference engine, or we can choose the Sugno rules to solve the particular problem. Okay, let us consider one simple example. Okay, let us take the vehicle. It's a bicycle. We can consider the two conditions of the system. The first one is the first variable is temperature. Normally the temperature conditions are freezing, cool, warm and hot. These are the four input parameters are considered. The first category, the temperature freezing. Let us assume the temperature is less than 50 degrees, 50 to 30 degrees, that is freezing condition, and the cool condition is make it as 30 to 70 degrees, and warm condition is 50 to 90 degrees Fahrenheit, and hot is the greater than 70 degrees. So we have the temperature membership functions are defined. The first membership function is temperature. It internally categorized as freezing, cool, warm and hot. These are the ranges are specified by make use of the membership function. So by make use of the membership function, let us assume the temperature is 36 degrees Fahrenheit, and at 36 degrees Fahrenheit we can analyze the situation. It is 30% cooling condition and 70% freezing condition. This is an individual element. By make use of the fuzzy membership function, let us assume 36 degrees Fahrenheit is there. The line is the vertical line is touching at cool line, and the second point is touching at freezing. By observing this, that 0.3 and 0.7, that indicating that the cool condition is 30% and freezing condition is 70%. We can we have to use the predicate logic. That means we have to maintain the relationship between two input variables or n number of input variables. You have to choose the predicate logic. By make use of the fuzzy logic connectivities, fuzzy conjunction or fuzzy disjunction. It's approximately equal to the AND operator, and disjunction is the OR operator. Normally fuzzy conjunction, it shows the least value of the selected input parameters, and disjunction is the highest value of the connected input members. Okay, here we can say fuzzy disjunction is A or B, that will give the maximum value of within the set of elements A and B, A or B. C is the quality, C is the disjunction of quality of A and B. Okay, let us assume the two parameters are here. A or B is equal to C. The C is equal to 0.75. How we will get this? A membership function is shown here and B is here. That is the first one is the A membership function representing 0.375, and B membership function is representing the 0.75. By combining these two, by make use of the OR operator, the largest value. What is the largest value? It is here is C is equal to 0.75. In the similar fashion, fuzzy conjunction, Here is the same problem. I have considered A and P is equal to C. Then naturally the lowest value. You see, this is the A is equal to 0.375 and B is equal to 0.75. That indicating that 0.375 and 0.75, which is the minimum value. 0.375 is the minimum value. Here the first one is the A is 0.4, 0.7. That is 70% of the value. 0.4 and 0.9, 0.7 and 0.9. A and B is equal to minimum of A and B. Here A is 0.7 and B is 0.9. Then by fuzzy AND operator, naturally this is the minimum value. So A and B gives a minimum value of A and A, B. Here is the minimum value is 0.7. Coming to our next problem, the speed control example. Let us consider the speed control example. How fast am I going to drive today? So depends upon the weather conditions. We can combine the input parameters. The first input parameter is the temperature, freezing, cool, warm and hot. And another one is the second one is the cloud covering. Inputs are temperature and cloud cover. So the first parameter, first membership function is freezing, cool, warm and hot. The ranges are already defined. Less than 50 degrees is freezing and cool condition is in between 30 and 70 and warm condition is 50 and 90. The greater than 70 degrees, that is the hot conditions. They are derived by make use of the triangular functions, and freezing and hot functions are represented in the trapezoidal functions. And cloud covering is sunny, partly covered and overcast. So 40% cover, less than 40% cover, that is sunny, and in between 20 to 80% cloud cover, it's a partly cover, and greater than 60% overcast. So based on this input two parameters, temperature and cloud covering, these two parameters, we can find the output. Output is the speed of the vehicle. So here slow and fast, we have only two parameters, speed, slow and fast. Less than 75 miles per hour is slow and greater than 25 miles is fast. But here is the overlapping is there, slow and fast overlapping is there, 25 to 75 miles per hour. These two parameters are the overlapping. We have to write the rules. If it is sunny and warm, drive fast. We are assuming that sunny in the sense temperature and warm condition, sunny and warm condition, drive fast. Cloudy and cool. Cloudy is the cloud cover. Cool temperature, normally slow. The driving speed is the combination of output of these two rules. Okay, here let us consider the example speed calculations. How fast will I go if it is 65 degrees and 25% of the cloud cover? So let us consider the first case, 65 degrees cold condition, that is the temperature condition. 65 degrees cool is 40% and warm is the 70%. You can check the parameters. Then horizontal line, the first line is touching at cold condition, that is approximately 40 degree 40% and that is 0.4, and the warm line is cut at the point is let us assume 7. That means when the temperature is 65 degrees, that is considered as a 40% cool and 70% warm condition. So another one is the cloud cover. Here is a 25%. The 25% line on x-axis, the cloud cover is represented in percentage. That is 25% means the first line is cut at partly cloud, and the second line is touching at sunny. That means 80% is sunny and cloud is 20%. So that is indicating per unit value is 0.8 and cloud is 0.2. So the first case, by make use of the 0.8 and 0.7, the minimum value is that is fast, 70% fast, 80% sunny cloud, and warm is temperature condition is warm. By combining this R operator, AND operator, the minimum value is 0.70. That means 80% cloud cover and 70% temperature. At that time, the vehicle speed is 0.7, that is 70% speed. Another one is the cloudy cover and cool. The temperature conditions normally we are represented as 0.2, that is 20%. So slow. The cloud cover is 20%. Let us assume that is 20, and temperature is 40% of the normal temperature. That is by combining these two input parameters, the speed of the vehicle is 20% of the slope. Then defudgification. Okay, but the previously we are discussed about the fudgification and defudgification. Based on that, those parameters, input parameters, and the functions or FIS rules, we can sort out the output condition. The output can be calculated by make use of this. So here 25% weighted 2 into 25%, the remaining is 7 into 75%. Combinedly 20% at a 25% cloud condition. Here is the fast is 75 kilometers, 20% and the 70%. Previously we are already calculated this. Here is the slow is 20% and fast is 0.7%. So here altogether 25%, less than 25 miles per hour is slow, greater than 75 miles per hour is fast. By taking this output thing, here is so 2 into 25 is 20%, another one is 70%. So 2 into 25 plus 7 into 75 by 2 plus 7 is equal to 9. The total the speed of the vehicle at 25% cloudy condition, 70% temperature case, 63.8 miles per hour. Here drawbacks to fuzzy logic. It requires tuning of membership functions. Requires the tuning of membership functions. Here is you have to select the input variables with different the number of memory functions. You have to select the number of membership functions and their tuning values. That means the range of the values is important. The range of the values must be now. Okay, suppose if you want to solve the problem, first of all, we have to identify the number of variables and the importance of those variables. Then you have to set the range of that particular fuzzy membership functions. That is nothing but a tuning. Then the next one is the fuzzy logic control. Fuzzy logic control in the sense where the control fuzzy logic control means and or operators are there. We have to combine the particular input parameters or input values with the use of or and operators. Those are the fuzzy logic control operators must be placed to identify the problem, to find out the solution. Deals with impression and vagueness and but not answer. These are the next. Another drawback is the vagueness. We don't know the exact output. We may not get the exact output. Suppose if you choose the conventional equations, you may get the exact output. But in the case of fuzzy logic controllers or artificial intelligence techniques, we may not get the exact answer. We may get the vague answer, but the result may be nearer to the actual value. Here come to the summary of fuzzy logic. Fuzzy logic provides way to calculate with impression and vagueness. Okay, fuzzy logic can be used to represent some kinds of human expertise. That means the previous experience, you can analyze the situation. We can take the decision accordingly. This type of information, that is by make use of the human expertise, you can use the fuzzy logic and the fuzzy membership sets and fuzzy linguistic variables. Know that the fuzzy and or operator and fuzzy controller, these are the summaries. Fuzzy logic provides way to calculate with impression and vagueness, and fuzzy logic can be used to represent some kinds of human expertise, fuzzy membership sets and fuzzy linguistic variables, fuzzy and or operator, fuzzy controller. Okay, here the sum of the references we can choose. Okay, is it here? Is it clear? Fuzzy logic. Okay, any doubts on this? Can I proceed further? Is my voice is okay? Ravindra? Okay, next coming to the, okay na? Okay, here now I am taking the one example. Which is taken from my PhD thesis. Here is the double lane transmission system considered for study and modeling. Hello.
Sir.
Disturbance is coming, but link. Okay, here this is one of the example. Let us consider one of the example which is taken. Hello. Okay, here one example I have taken double line transmission system considered for study and modeling. How the transmission line system protection can be visualized by make use of the Simulink environment with the help of wavelet analysis. Here my transmission line system containing the 210 kilometers in between two buses, bus 1 and bus 2. The first of all we have to construct a Simulink diagram. Let us see how we can construct the Simulink diagram. Okay, first of all, we have to consider the parameters for the test power system. Here is the two generators at bus 1 and bus 2. Here is at bus 1, one generation is there, and bus 2 at generation, another generation is there, and the transmission lines are parallel transmission lines. The parameters are collected at GPS satellite. The currents parameters are collected through GPS satellite. The wavelet based detector and classifier is attached here on both sides, the bus 1 and bus 2. Fuzzy based locator is normally the transmission line protection. We have to identify the type of fault is occurred, whether the fault is single line fault or double line fault, and three phase faults are there. The detection of fault and discrimination of fault. Detection of fault in the sense within the 210 kilometer transmission line, is there any fault occurred? That is detection. Discrimination in the sense what type of fault it is. If the fault is related to the single line to ground fault or double line to ground fault or three phase fault and double line faults. Single line to ground fault in the sense the fault is occurred in between A to ground, B to ground, C to ground, and double line faults are AB ground, BC ground, and CA ground. And double line faults are AB, BC, CA, different combinations. So you can analyze. That is nothing but a discrimination, and the location where the fault is occurred within the 210 kilometers of transmission line. For this purpose, first of all, you have to design a Simulink model. So first of all, you have to the realistic parameters. The generator capacity is 500 kV. See, this power is unlimited. Let us assume it may be 9,000 megawatts, and generator 2 also the same. The power X by R ratio, reactance and resistance ratio is 10, and phase angle is 10 degrees. Here is at generator 1, and generator 2 phase angle is at A is 20 degrees. So the phase angle must be the difference must be there, otherwise the power may not transfer. This is a self-loading transmission system. We know that the transmission line containing the parameters, positive and zero sequence components are there. Resistance R0 is the zero sequence resistance 0.3864 ohms per kilometer. Positive and negative is 0.01273 ohms per kilometer. So inductance and the capacitance parameters are identified in the transmission line. Distributed parameters are identified, and to find out the fault analysis, to find out the fault, we are using the wavelet analysis. for that wavelet analysis, we have to consider the different parameters. What is the type of wavelet we have to select it. Mother wavelet, here is the Bayer 1.5 and sampling frequency 216 kilohertz. How we will get the 216 kilohertz is nothing but a 60 Hz frequency and 32 samples. So altogether it becomes the 60 into 32. It's equal to 216 now. Our waveform is divided into the number of sections. That is 180 degrees of waveform is divided into 32 sections. The frequency is 60 Hz. So 32 into 6, 260. That is the each and every piece of the waveform is again divided into the 100 samples. So total sampling frequency, that is 216 kilohertz, and information analyzed by make use of the Bayer 1.5 D1 detailed coefficients. The frequency band is in between 54 kHz to the 108 kHz, and the number of samples per cycle is 3600 samples. Occurrence of fault, initially the first cycle we are leaving because the settling time it may be approximately one cycle. So we are considered the fault at second cycle. The data window length is one cycle, that is equal to 17.7 milliseconds. These are the parameters we have to select. The first one is the system parameters, and the second one is the details of wavelet and associated parameters. Here the transmission line is designed by making use of the different sections are there. Here is the first section. The top one is 210 kilometers, and the fault is this is 105 kilometers, and by combining these two 105 kilometers, the combinedly 210 kilometers. Upper one transmission line is 210 kilometers, and the lower one is the 210 kilometers. Suppose if we want to place the fault at 40 kilometers, then the section 1 is 40 kilometers, and the section 2 is the 110, 105 plus this is 145. The total the fault is located here. By make use of the fault block, we can select any type of fault. Okay, three source. Here is the block parameters or sources are there. The first one is source. Here is the 500 kilowatts and 9000 MVA capacity. Source is connected here. The first source, and similarly the second source. We are maintaining the phase difference. Here is the first one is the 0 degrees, and the second one is the 20 degrees. So that the system is self-loading condition. Without connecting any load, we can represent the simulation diagram by differentiating these phase angles. Okay, the three-phase source is the first one is the 500 e to the power of 3, that indicates the 500 kV into 0.98 is the RMS value. We have to consider the RMS value. That's why the factor is 0.98 is taken. A phase angle of phase A is 20 degrees. Frequency is international standard frequency 60 Hz, and three-phase short circuit level of base voltage is 9000 E6, that is MVA rating, and base voltage is 500 kV. X by R ratio is 10, and the second one is the next one is the transmission line. The transmission line containing number of phases are 3. Frequency is 60. Resistance per unit length is R1, R0. That is R1 is the positive sequence resistance, positive sequence impedance, and positive sequence capacitance. All the parameters are represented here. Line length is represented instead of writing the number. Now the line length is I am taking it as a km1 is that is a variable. The variable is initiated in the program. Here the block parameters, 3-phase fault resistance is 15 degrees and ground resistance is 0.01 and the transition states are 0, 1. 1 indicating the on and 0 is the off. Transition time, here is I am using the transition time in the sense the fault is varying, depends upon the fault inception angle. That means we can in the program itself I am defining the transmission time TT, transition time TT variable. We can change the fault inception angle in the by make use of the program. Okay, the parameters are set in the 3-phase fault block and voltage and current parameters are represented here. The B22, that means B11 and B22 is there, IABC and VABC, that means collect the voltage and simultaneously the current. Base power is 100 MVA rating and base voltage is 500 kV. And configuration parameters, by clicking the configuration parameters we can set, and we have to consider the simulation type is discrete and sample time is 1/21600. That means this 216 kilohertz, 216 kilohertz, which are already calculated by make use of the number of samples. Our waveform is one waveform divided into 32 samples, 60 Hz frequency. Every sample again divided into 100 samples. So that altogether 60 into 32 into 100. So totally 216,000. Here to calibrate our system, VAB11 and VAB-B22, these the first bus and the second bus. The parameters are 11 and 22. These are taken from the measuring blocks, and this we can make use of these. We can find out the waveforms. Fault analysis can be visualized, but this is not sufficient to analyze the fault. So these all the parameters are transferred to the workspace. So we in the VABC containing the VABC meant voltage at ABC phases. The parameters are transferred to the workspace, that is VA1, VB1, VC1. These are the workspace related to the voltage, and IA1, IB1, IC1. This is the workspace related to the current parameters. By make use of these workspace collected parameters, we can analyze the system. The first one as well as the second one, bus 1 and bus 2. Okay, here the Simulink code. Now I am presenting the Simulink code. So this is one latest methodology to analyze the simulation parameters to program. So normally in the previous cases this is one of the latest technique. Why? Because normally the simulation diagram we can analyze the parameter visually, but we may not collect the information. The information must be stored in the workspaces. But in this program we can combine simulation as well as the programming. The simulation parameters directly we can access and we can analyze and find out the solution. So here is the Simulink code, CLC clear all. That means clear the command and clear the command window. And the next one is open grk transmission linux.mdl. That is the simulation file I am calling here. We are calling the by make use of the open built-in function open, the model file is called here. In that the parameter previously we are observed the parameters here IA1, VA1, IA1 like that voltage parameters and current parameters. But unfortunately in my project I am taking only current parameters. That's why I am taking the only current parameters IA1, IB1, IC1 and IA2, IB2, IC2. The parameter 1 indicating that the bus 1 and the IA2 is the 2 indicating that the bus 2. These two parameters are collected from the workspace by make use of these type of commands. Here my transmission line is 200 kilometers. Let us assume the KM1 is 80 kilometers. Then naturally KM2 is there, that is 120 kilometers. The KM1 is now in this case I created the fault at 80 kilometers from bus 1. Okay, here TT transition time is fixed here, but we can change the transmission line. Normally the transmission line is 1 by 2160. That is 2160 is generated 32 samples and 60 Hz frequency. Based on that we can find out the fault inception angle. Here is the fault inception angle is fixed by setting the TT value. Then previously we are called the MDL file or SLX file. MDL is this program is related to the 2017 model. Suppose if you want to run the same program, the model file can be changed into the SLX. The first is we are called open is we are opening the model file or Simulink model file, and SIM indicates simulate that particular file. The name is already indicated here. First is opening is completed. We are setting the input line parameters and fault inception angle parameters are set, and then we are simulating. Then set parameters is set param indicating that the initialization of the system by make use of the gr file, gr.m file is there. So we are calling the initialization parameters by make use of the set param, means set parameters. GRK transmission line X indicates this is the model file, and preload function is we are loading the particular input parameters by make use of the set param. Okay, here the next statements are okay. First one is the group of statements. Here is the group of statements are related to the wavelet decomposition. So wavelet decomposition, lower and the higher. Okay, this is these commands are related to the wavelet decomposition coefficients IA1, IB1, IC1. This is the current, and wave. The first one is CIA1 and LIA, lower and the higher frequencies. So suppose if you consider the 500 hertz frequency, 0 to 125 is lower, and 126 to 500 is the higher. So divided into two parts, lower and the higher. So wave decomposition to lower and the higher. Wave decomposition IA1 is the current parameter, which is the data is collected from the wave IA1 and IB1 and IC1. All these are connected from the workspace of bus 1, and IA2, IB2, IC2 is the workspace of 2. So one is indicating the first level coefficients. Bayer 1.5 is the mother wavelet. So we are using Bayer 1.5 is the mother wavelet. IA1, IB1, IC1 is the current parameters. And the next step is wavelet decomposition and then detailed coefficients. The detailed coefficients are calculated by make use of the lower and the higher values frequencies, the first level coefficients. Wavelet decomposition. After that, we are calculating the detailed coefficients. So the first one is after calculating the detailed coefficients, how you can find out the fault. Normally, the fault is occurred nearer to the bus 1. The naturally the difference whenever the fault occurs, the difference between the current is bus 1 and bus 2. Whenever the fault is occurred at nearer to the bus 1, the naturally the bus 1 current is larger than the bus 2. So naturally the difference is there. Whenever the fault occurs, there is a current difference between bus 1 and bus 2. So we are calculating the CD1 IA indicates the fault is calculated. The fault current is calculated by make use of the detailed coefficients of bus 1 and bus 2. The difference is calculated. CD1 IB and CD1 IC. That means the phase A, phase B, and phase C detailed coefficients are calculated. Then we can measure the parameters by make use of the plots, subplots. 337 indicates the 3 rows and 3 columns. Subplot indicates the normally we can plot the number of plots on a single sheet. In this case, 337 indicates the normally we can in this case 3 rows and 3 columns. The subplot 331, that means the first element is the first subplot is 331 and the second plot is 332, like that. It's like a matrix we can arrange the subplots. So here is absolute values of the previously. It may generate the negative values. CD1 IA, CD1 IB, CD1 IC. Maybe positive negative values may occur. Those values are taking the absolute values. Then we can plot these subplots are 331 and first position, second position, and third position. We are drawing the plots, absolute plots of detailed coefficients. Here is some of the detailed coefficients. So we are using the technique. Whenever the fault is occurred, the fault can be highlighted by make use of this technique, some of the detailed coefficients. So our parameters are taking, the different parameters are taking the sections. 8 sections we are considered, 8 times we are calculated. That is we are using the sum of the detailed coefficients by moving window technique. The window is moving within a cycle 8 times. That is moving average technique or moving sum here is. Next index IA, sum of the detailed coefficients. By make use of the sum of the detailed coefficients, we can find out the fault within a short duration of time. So subplot 334 indicating that original values of the current signals of terminal 1 and terminal 2. Subplot 334 and subplot 335 is showing the original current signals, and subplot 336 it's indicating the sum of the detailed coefficients of phase A, phase B, phase C, so that we can analyze the faults. Here is the first one is the detailed coefficients, first row is the detailed coefficients, and in the second row original current waveforms of bus 1 and bus 2, and the next second row third graph is related to the to identify the fault, and fourth one is the detailed coefficients of normal detailed coefficients. Okay, let us assume by observing this plot diagram, here is the first one is the detailed coefficients are varying 0 to 1000, and the second one is 0 to 200. It's may hardly the maximum value is 150, and third graph is first of third graph is detailed coefficients is hardly it's also 150. But by observing these three, first one is the phase A, phase B, and phase C. By observing this diagram, we can find out the fault in the phase A. Why? Because the detailed coefficient value is highest when compared to the three values. This is 1000, and the next one is 150, and the next one is 150. Which one is the higher? The first one is higher. That's why we can identify that the fault is located at phase A. And by make use of the original current signals also indicating that one waveform is a completely sine waveform, that is 5000 amperes, and the second one is the negative is also there. Okay, here is 5000, the next one is 2000, and next, these two, by comparing these two, the fault is nearer to the bus 1. We can identify that by observing the original current signals. We can identify that the fault is in between the lines bus 1 and bus 2. Bus 1 is showing 5000 amperes maximum current. Here is 2000. That means the fault is nearer to the bus 1. Okay, here the next one, second row, third graph indicating that 4000 fault index value is more than 4000. So by make use of how, the first thing is how we can find out the fault within a short duration. By make use of the amperes original current signals, the fault is located, it's approximately 40 milliseconds. It's approximately 40 milliseconds. But in the case of fault index, by make use of the fault index, we can find the fault at it's approximately 14 milliseconds. So normally the current signal, it may takes around 40 milliseconds, and here it is taking around only 14 milliseconds. That means we can find the fault very fast when compared to analyzing the current signals. This is the detection and discrimination of the fault. Okay, here can say that the fault is the faulty phase signal is more values when compared to the healthy signals. So this is the current signals are considered, calculation of the coefficients, the algorithm indicating that the determination of currents and calculation of coefficients, and sum of the detailed coefficients. By comparing the sum of the detailed coefficients, we can get the A to ground fault, B to ground fault, C2 ground fault, and similarly ABG, ACG and BCG faults. So we can find the all types of faults by make use of these algorithm. Okay, here is a single line to ground fault as bus 1, single line to ground fault, and here is the double line to ground fault. So by current signals, the ABG fault is at 40% of the transmission line. That means 40% in the sense 200 kilometers. 40% means 80 kilometers from terminal 1 or bus 1. Okay, here this is two waveforms are showing the higher values when compared to the red signal. So the fault is at a double line fault. Then by observing this, by observing the detailed coefficients of current signals, these are the 1500, CD1 AX and CD1 BX is values are 1500 and this is also 1500. This is 80, that indicating that the fault is located at the phases A and B, and similarly we can observe that the ABG fault by make use of the sum of the detailed coefficients, that is sum of the fault index is derived by make use of the sum of the detailed coefficients. Okay, the next part is the location of the transmission line. So location of the transmission line, by make use of the fuzzy logic, we are identified the fault location S1 and S2. The S1 is the parameter is related to the bus 1 or terminal 1. S2 is related to the bus 2 or terminal 2. Location of transmission line, we are using the Mandamini fuzzy inference system output parameter. Here is the S1 and S2. These parameters are the input variables are the detailed coefficients and the output variable is distance. So we are providing the relationship between the detailed coefficients and the distance by making use of the Mandamini fuzzy inference systems. In this Mandamini, we are using the different types of fuzzy rules are added here, and the first input is very low. The value from that is detailed coefficient values are very low, low, medium, high, very high. For these categories are defined with the specified ranges, and this is related to the input variables S2. That means the terminal 2. These are the output parameters. The output is the distance 0 to 1. That means the percentage 10% of the transmission line, 20% of the transmission line, 30% of the transmission line, 40, 50, 60, 100. That means 210 kilometers are calibrated by making use of the per unit quantities. So our wavelet detailed coefficients and the distance, all the parameters are represented per unit. So this is the variation of the fault index. The inception angle is 20 degrees. The distance is varied from 0 to 200 kilometers in steps of 10 kilometers. So at 10 kilometers, that is the fault index is 0.2. The value is varying from 0.2 to 1. The circle indicates the terminal 1 and star indicates the terminal 2. These two are the distance between the fault is varying, and fault inception angle 20, and the next one is the line to line fault. This is LG fault and this is line to line fault, and very high linguistic variables. By linguistic variables are derived very high, medium, high and low. The similar fashion S1 and S2 and linguistic variables to the distance. So we are providing the relationship between the input variables. The input variables are the wavelet detailed coefficients. The output variables are the distance. We are providing the relationship by making use of the table. So here this is the first one is the input parameters. First two are the input parameters at bus 1 and bus 2. This is the output. So A to ground fault, actual distance we are taken the parameters at 20 kilometers by make use of the fuzzy logic controller. The distance is 26 kilometers. So here is error is 6 kilometers. Here is error is let us consider the 200 kilometers. Error is 3%. The next one is actual distance is 40 kilometers and fuzzy distance is 40. So here is error is 0. Like that, we are tested almost all the faults AG, BG, BC and ABCG. So this is the theoretical description about our MATLAB. Okay, let us take 5 minutes break. Then I will show the simulation diagram which I have considered how to run the MATLAB files, how to combine the Simulink as well as the MDL file.
Thank you, sir. Thank you very much. All of you may take the 5 minutes break, and sir will show you the simulation file after 5 minutes. Thank you. Thank you very much. Please be online. It will be a quick break. Thank you.
Okay, here let us start our simulation, right? Start Siddhama.
We'll start, sir.
Okay. Okay, here this is the which I have already shown the code. కనిపిస్తుందా రాజేంద్ర స్క్రీన్ కనిపిస్తుందా
కనిపిస్తుంది సార్ కోడ్ ఓకే కొంచెం మాక్సిమైజ్ చేస్తే సరిపోతుంది
మాక్సిమైజ్ కాదు మాక్సిమైజ్ అవదలేదు అంతే అలాగ వస్తుంది అంటే మనం ఇందాక ఆల్రెడీ దిస్ కోడ్ ఈజ్ ఆల్రెడీ ఐ హావ్ షోన్ టు యూ here is the first one is the CLC CLR all GRK transmission line X. The files are located here. Okay, first one is the set parameters, set param GRK transmission line X GR. Here the gr.m file is initiating the transmission simulation time is initiated. TS is equal to 1 by 216,000. TS2, TS1, this is the first one is the simulation of our system file and the simulation of internal components. These two are defined separately. Here is the, now I am running this. So TS and TS1 already initiated. Then afterwards the transmission line dot m. In this case we are calling the simulation file and simulation of after opening the simulation file we are simulating that file. So now I am running the show. See, automatically the file is called here. Automatically it will run the file. Here I have placed the fault is at A2 ground fault. Here is the A2 ground fault. After running the simulation, see, we will get the parameters. See, it's a A2 ground fault. Okay, let us check the one more analysis. Now I am placing the AP to ground fault, selecting the A and P. Okay, then save. Then again I am running here. Then opening the file, see, you can observe the see this is will get the double in fault. It's 1500 and 150. See, by observing this. Okay, and this by make use of the amperes original current waveform, the fault is located at 40 the time is required to find out the fault is 40 milliseconds. In this case, by make use of the fault index, by make use of the some of the detailed coefficients, here is it's around 14 x is 14. See, we can observe the x is an x-axis 14. So 14 milliseconds we are find out. In similar fashion, we can analyze BC fault, apply, okay, saving. Okay, see this. Here is the BC fault. There is no any ground. So B and C are the overlapping here. So B and C, these two waveforms are similar. That means the fault is at BC value. If the ground is incorporated, then B and C variations are, we can observe the variations in the B and C. Okay, and then coming to the location of the fault, on the command prompt at the command window, just you can try fuzzy. It will open the fuzzy logic designer block. You can open import from file. This is a location of location. So this is our my original fuzzy logic to find out the location of the fault. So this is the input parameter, first input, very low, low, high, very high, and very, very high. This is number one, and the second waveform is looks like this. Input 2, very low, low, high, very high, and very high. And the next one is the output is defined here. Z0, Z1, Z2, that means zones we are defining here, 0 to 20% of the transmission line, zone 1 or Z1, 10% to 30, zone 2, like that where output is defined here. And then this is fuzzy logic rules are written here by selecting the first input and the second input and then output. These are the rules are framed here. 31 rules are written. Okay. Then we can use the surface viewer. See our number of input parameters and the output parameters, combining how these interrelated by making use of the fuzzy logic rules which are written in the Mendamini FIS fuzzy inference system. See, these two are the input parameters and these are the output parameters, and we can change the value. Suppose if you change this value, automatically the parameter is changed here. See, 57, based on the rules, the output parameters are changed. If we change the input to simultaneously, here is 75% of the transmission line. The output parameter is depends upon the input parameters of the input membership functions. The output is depends upon the input membership function. Now I am wearing the line here. See, here is 0.56, 0.65, like that. You can observe the relationship between the input parameters and the output parameters. Okay. And similar fashion, import from file. I am using in the previously speed of the vehicle. Here one input parameter. This is freezing, cool, warm, and hot. And this is sunny and partly cloudy and overcast. And the output is defined here, slow and fast. Surface viewer. And another thing is the rule viewer. So change it. Suppose if you change the input parameters, simultaneously it will change the output. See how input parameter 76.2 and input 1 is 76.2 and input 2 is the 50%. Then the output becomes the 70.5 kilometers. The first one is the input one is the temperature, and input 2 is the cloudy conditions. So see the values how it is changing. 58.4. Suppose if you change the input one, automatically that will reflect into the, if you change the any one of the input, that will reflect to the output. Okay. Like that, we can solve any type of problem without knowing the relationship between mathematical relationship between output and input. Okay, this is MATLAB. If you have any doubts.
Sir, one of the participants asked about one question, sir.
Okay. Okay.
How you sizing the components like that? He asked.
How is
Sizing the components.
sizing the components, that is based on the sizing the components in the sense, and what sense he is asking? Transmission line or any?
1 minute, sir. All the participants, you may ask the questions right now. I'm giving the permissions to each and everybody to you for ask the questions. Now you may ask the questions if you have any doubts. Babita Nanda, you may ask the questions directly yourself.
Sir, when good afternoon, sir. This is Babita, sir.
Okay.
Sir,
Okay,
like the parameter you have taken, the transmission line parameters, all the components, like how you calculated, like any mathematical equation is there, or
yes, mathematical equation is there, and we are consider the research papers. We are taking the data from that IEEE standard research papers, and some of the parameters to be calculated.
okay, sir. And sir, that physiology controller you are using, in
Okay.
that, if I will use that controller in battery bank, suppose two battery bank is there, I want to
Yes.
size.
Okay, we can
Like I am using in the wind farm, sir. So
okay.
in that I am using this physiology controller. So in that, how
Okay.
you are
Okay.
yes, sir.
Actually, suppose if you choose two inputs, then in this case, suppose if you are choosing the voltage low, medium, high, like that, you can select the three quantities. Low is, let us assume, less than 30 volts, and medium is 20 to 50, like that,
Yes, sir.
triangular or trapezoidal. The first of all, you have to select the range of that particular member function. First of all, select the how many number of member functions and the member function distribution. That means how you are divide the particular values. Then based on that, you can write the rules of the fuzzy logic. If voltage V1 is low, very low, and let us assume wind is the wind velocity is very low, then naturally the voltage becomes the less. So finally you can calculate the efficiency. The first one is first input variable is related to the wind, and the second one is related to the that is PV. Let us assume, suppose
Yes, sir.
integrating the based on that you can formulate the fuzzy rules. Here is in the fuzzy logic, the important thing is what are the variables you have to select, and the range of those variables, how it differentiate the parameters. the condition of the situation. So low voltage, high voltage, and what cases you will get. Normally in the case of PV cells, radiance or temperature, like that, so many parameters are there. But anyhow, we may consider the 2 or 3 parameters. From that, you can find out the output. The output is based upon the input parameters. That is, we know that. But unfortunately, some of the cases, we may not get the equations in between. Equations are mathematical equations in between output and the input. Why? Because the radiance value is not fixed. The temperature is varying within 24 hours, different time quantum. Based on that, you can analyze the system, then you can select the input parameter so that you will get the required output. Okay, madam?
Okay, sir.
Okay.
Thank you, sir. Thank you.
Okay.
Sir, shall I conclude the session, sir?
Okay.
Thank you very much, Vikmar sir. Thank you very much for your accepting our invitation to act as a today's resource person and for giving such a valuable information about the MATLAB. Thank you very much, sir.
Thank you.
All the persons, we will send a feedback link through email only. So all of you have to submit the feedback must and should, and we will take the attendance at each and every session. If you participate in each and every session only, you will get the certificate. You will get the certificate. Thank you one and all.
Sir, can you share this video later on or?
Okay.
Yeah,
Okay.
we will share this video in YouTube, madam. You can directly download from the YouTube
It
after the
will
completion after the completion of all 6 days, madam. Not
yes.
tomorrow.
Okay, okay. It will be fine, sir. Thank you.
Okay.
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 Thank you.
Thank you.